Hey guys, hope you're all doing good and welcome to a new video. So today we are going to be discussing the results that we obtained from running the 2D cavitation simulation. So I'll first get started by playing this video. I'll play this video once and then play it again, and during the second time I'll discuss the results. Alright, so let me just play this one more time and I'll just pause. So here we have 4 different plots. The most important plots are the first 3, 1, 2 and 3. The fourth plot is a derived plot. In the first plot, what you're looking at is the velocity magnitude. Now given that this is a nozzle, the majority pressure drop is going to be occurring at the throat, correct? And since that's where majority of the pressure drops, you can expect the velocity to be maximum there. So that's where the velocity around that region is around 120 meters per second. But here you can see that there is also this smaller region where the velocity is really low, correct? Now this region is where your pressure also becomes low because of the sudden contraction, okay, and this is where you would expect cavitation to take place. The static pressure in that area drops lower than the vapor pressure of the liquid, which is C14H30, which causes C14H30 to vaporize, and this can be seen in 2 ways. So first you can actually see the value of alpha showing up. So whenever alpha is 1, that means you are dealing with gas phase, and whenever alpha is 0, that means you are dealing with liquid phase. So that's why in this region you can see that alpha is 0, which means it's purely liquid, and near this sharp corner you are actually seeing contours of vapor, and near the sharp corner you are seeing contours of the vapor, which is represented by alpha equal to 1. Now in this video we are actually showing you the vapor C14H30. Note how before the entrance of the throttle there is no vapor, and at the throat the vapor is starting to form and it's just going to flow along. Now the reason why it's interesting to study cavitation is physical systems like fuel injectors have cavitation taking place in them a lot, and if you take diesel injectors, the injection pressure are so high which makes the pressure drop high as well, and that can actually cause a lot of cavitation. Now the thing with cavitation is that it's not essentially bad. Yes, it does affect the life of the part, but the more important thing that it actually affects is the fuel flow rate. So for example, if I play this, you can see how the mass flow rate is actually changing, correct? You can see that it is continuously fluctuating. This fluctuation in mass flow rate can affect the system's performance. For example, if you're taking a diesel engine, you experience something called as mixing controlled combustion, right? So in other words, combustion is predominantly how the spray atomizes and then converts to vapor. So if you have fluctuations in how the fuel is actually coming into the combustion chamber, the vaporization characteristics and also combustion characteristics will be affected, and that is why it's important to study cavitation. For this particular case, we ran a 2-dimensional model with adaptive mesh refinement based on the vapor species. So you can see that our peak cell count is around 18,000 cells, and then after that it kind of reaches a steady state. So this is basically the steady value for this particular problem. Now depending upon the amount of cavitation and the subgrid scale criteria, you can actually either increase this or decrease this. And just as a sanity check, we also looked at the mass flow rates at the inlet and outlet to make sure that we are getting convergence. And here you can see that there are a lot of fluctuations in the outlet mass flow rate. That is expected because you are actually having cavitation, and at the inlet the mass flow rate is more or less the same. Now here you can actually look at the two numbers together, 25.8379 and 25.7829. That's actually quite close to each other. The final plot that I wanted to show is actually very interesting, and this is something that a lot of engineering companies do. And let me first play this. So you can see that I'm running the simulation here. Now the first 3 plots 1, 2 and 3 are pretty much the same. What is really interesting is the last plot here. So what I'm doing is I've created a line probe, and I have created a line probe on the throat, and I'm looking at how the mass flow rate across that line probe varies. Now this is really important because in most of the simulations where fuel or some type of water is being injected, we say that the mass flow rate is steady or we give it a very ideal profile, but in real life it's not like that. In real life it can actually fluctuate quite a bit, and it's a time varying quantity, and that is why whenever you want to run a simulation where injection is critical, you need experimental data on rate of injection, and that data should be fairly accurate. So here you can see that depending on the time, the mass flow rate across the line changes. So if you have experimental data which provides you this information, you can take that and you can feed that into a simulation as an input, and you can obtain good simulation results for the injection part. Alright, that being said, we have posted a small tutorial on how to do this line plot in the link below. Please take a look at it, as you will be requiring that for your assignment. With that, I would like to conclude this video, and I'll see you guys in the next one. Bye.